You are witnessing film of the first United States satellite, Explorer, being launched into outer space. The State University of Iowa today presents another in its series, At the Frontier. Here is your host, Professor H. Clay Harshbarger.
In January 1958, all of us were thrilled when our first satellite, Explorer 1, began to orbit about the Earth. Here at the State University of Iowa, our thrill was perhaps a little greater because instruments designed and built here on campus were flying in Explorer 1. I'd like you to meet the man under whose direction these instruments were designed and built, Dr. James Van Allen, head of the Department of Physics at the State University of Iowa. Professor Van Allen is a native Iowan. He graduated from Iowa Wesleyan. He did his graduate work at the State University of Iowa. Dr. Van Allen is chairman of the National Committee of Instrumentation on board all the satellites this country will put into outer space during the current geophysical year. In short, the instruments which will send information back to Earth to the scientists in this country. Jim, I've been doing a small and very unscientific sampling of questions which people have about satellites. I gather that one of the questions which is most frequently asked is, how do you actually get one of these into space, and then how do you keep it there?
Well, Dr. Harshbarger, it's a pleasure to attempt to answer that question because it is a very commonly asked one. The principles of how to put an object into outer space, into an orbit around the Earth, have been understood for a great many years. In fact, I have a book here written by Sir Isaac Newton, published in 1686, completely in Latin. Now, on one page of this book, Newton gives a diagram which is an explanation of how this is possible in principle. And I think Newton's explanation has still not been improved upon. And I should like to repeat his explanation with the help of the blackboard to show how this goes.
Very good.
So, here's the scheme as discussed by Isaac Newton to illustrate the possibilities of making an Earth satellite. This is 1686.
Yeah.
Now this circle represents the Earth, and Newton imagined for the purpose of illustration that there would be a very high mountain here at some point on the Earth. Now he said, let's imagine the following. First the man stands on the top of the mountain and hurls a rock from there as fast as he can throw it. Now, as the rock flies forward, it also drops due to the attraction of the Earth and falls in a trajectory, something of that sort.
This experience is common.
Yes, this is an everyday experience. Now, next, although Newton didn't consider a rifle, I might consider a rifle here, and let's fire a rifle bullet considerably faster. Now, it will also fall the same distance per second as the rock, but in the same length of time, it travels a good bit farther, naturally. Yeah. So the trajectory of a rifle bullet, let's say, would look more like this.
Yes.
Now, continuing, the trajectory of a very high-velocity cannonball might resemble this one. Now, if one continues this process and fires more and more high-velocity objects, you can see that you come to the case resembling this one, which doesn't manage to hit the Earth at all, but continues around, and this one we would call an orbit around the Earth, but it is a natural extension of the throwing of a rock. Now, this object falls toward the Earth in the same distance per second as does this one, but meanwhile, it's moving forward a great deal faster, so it moves far enough so it never quite hits the Earth. It's like a hound chasing a mechanical rabbit on a racetrack. He never quite catches it. Now,
excuse me, now I take it the one that's in orbit we could now say is Explorer 1.
Yes.
Now about Explorer 2.
This would be Explorer 1. Explorer 2 might very well be represented by this case.
In other words, in Explorer 2, enough velocity was not attained to get it into orbit.
That's correct. That's the simple deficiency in velocity. In all other respects, it would have performed very similar to
Yeah.
Explorer 1.
Now, I find that there's another question, Dr. Van Allen, that people frequently don't quite understand, and I'm sure I don't either, and that is why it never appears overhead at exactly the same point on successive orbits.
Yes, well, that I think we might illustrate that with a globe, because it is a little more complicated question. Now, here we have a model to illustrate the nature of the orbit of a satellite with respect to the Earth. Now, in the first place, one should understand that the Earth itself will be rotating slowly. Let me illustrate it in this way. And now that's one part of the problem and of the consideration. Yeah. The other part is, let's represent this wire as representing the orbit itself. Now, the satellite may be imagined as a bead sliding along this orbit. So the combination of the two motions would be of this nature. The satellite would be rapidly moving along here, the Earth slowly rotating inside. So you can see that the satellite overtakes and goes much more rapidly than the Earth and passes by in this fashion. So this would be a sample of the actual dynamical motion of the system.
Yes.
Now, perhaps another way to look at it might be on a chart of the Earth. And this is a Mercator projection of the Earth. And as a specific illustration, this is the actual chart we used in considering when to expect the Explorer 1 to appear over various stations on the Earth. This is the actual chart I used.
In other words, this is something of a historical document.
Well, it is to me, at any rate. This is the chart I calculated in advance and used it on the evening of January 31st this year to understand at what times and positions we might expect the first reception of the signal. Now, this represents the launching point on Cape Canaveral in Florida. The initial flight was intended to be in this general direction. Now, this is the projection on a map of the same type of motion we were looking at here, with the bead moving on the wire representing the orbital trajectory. And now, the amount of motion of the Earth from the launching time till the next time around is represented actually by this amount. That's the amount the Earth rotated while we were going around in the orbit. Now, the total time around, as it turned out in the case of Explorer 1, was about 115 minutes, so almost 2 hours. So this is the amount the Earth rotates during 2 hours.
Yes. Incidentally, how were your calculations in terms of the points on the surface of the Earth?
Well, as it turned out, all of my times were too soon, actually. We expected it at every point somewhat sooner than it actually got there. And in terms of Newton's discussion, again, this was because the velocity turned out to be rather better than the expectation, and it went out farther and took longer.
Yes.
But,
now, another question that I gather people sometimes ask is that instead of having this go around every 115 minutes, why not once a day or once every month?
Yes. Well, this question was also discussed by Newton, and in terms of our diagram on the board, if the velocity is too low as it starts, then it will not go around. So there's a certain minimum velocity required in order to make a satellite for an object, the Earth. For any other object, for example, there could be a satellite of the Moon or of any other gravitational object. And the velocity required is a characteristic of the body in question, its radius and its mass. Now, if one would like to have a slow satellite, then one must put it out very much farther and must start it much more rapidly. For example, the Moon is our only known natural satellite of the Earth. It requires 28 days to go around the Earth, so that's a real nice slow one, but it must be at a very great distance.
And the rate is faster than, say, Explorer 1?
The actual linear velocity is much greater, but the period is much slower because it's so far away.
The orbit is much greater in diameter and circumference.
And for example, it's easy to calculate that an orbit at a radius of 22,000 miles from the center of the Earth would go around in exactly 1 day. And that would be a rather interesting special case.
Well, why don't we sit down for a minute, Dr. Van Allen? I gather from reading the newspapers and the magazines and listening to people talk that This Explorer has gotten all mixed up with Russian Sputniks and military and all kinds of things, and national pride. Is this a military program?
Well, no, it's not a military program in general conception or in purpose. Now, the military services are supplying a great deal of the so-called hardware, the propulsive units, and the logistics required to conduct a worldwide operation of this sort. And of course, that at the present time is an essential aspect of the actual accomplishment. However, the purpose of the work is a scientific one, and it's very nearly pure scientific experimentation.
Would you say a small paragraph on the basic research part of this?
Yes, all the experiments we are doing and planning for the satellites in this country come under the heading of quite pure research. In no one of the cases is there any immediate application of a practical character. The spirit of all of these investigations is to find out what the world is like, and as one man put it, to climb to a higher cherry tree and see a little farther in the world. So that's the motivation of this field, is to understand more about the geophysical nature of our Earth and its astronomical environment.
In other words, the satellite is the highest cherry tree that man has managed to climb to the top of up to this point.
Yes, that's correct. Yeah.
Now, your own interest in this program, your own personal interest is what?
Well, principally in the cosmic ray observations, yes.
Now, we've all heard a great deal about cosmic rays. What are cosmic rays?
Well, cosmic rays are very high-energy particles coming to us from outer space someplace. They really are the original outer space bodies, so to speak, that reach the Earth. And the cosmic ray beam consists mainly of the nuclei of hydrogen atoms and the nuclei of heavier atoms from the chemical periodic table.
So I suppose you could think of these as little pieces of, in a very unscientific way, little pieces of hydrogen and iron that are flying through space at great velocity.
Yes, the smallest possible pieces, individual nuclei.
Yes.
It's sort of like a pinch of material broken down and then speeded up to very great velocities, and these pepper all over the Earth.
Yes. Now, why do you have to go out into outer space to investigate these?
Well, the main reason is that our atmosphere, of course, the atmosphere at any one point is quite tenuous, but if you sum up the whole atmosphere of the Earth, it's equivalent to a layer of water 30 feet thick. So that, in effect, we're doing experiments and doing measurements here on the Earth under a blanket of water 30 feet thick. Now, the nature of the radiation has changed very profoundly in penetration through that layer, and what we finally see on the Earth is only the rather dim descendants of what we start out with. So, in the first place, we must go to high altitudes in order to study the original radiation. And in the second place, the satellite stays up there a long time and covers a tremendous geographical area of the Earth.
Now, your own personal interest is in, perhaps this isn't the right word, but mapping the cosmic rays in their frequency and energy in outer space?
Yes, that's exactly what we're up to. We're undertaking to make what we call a cosmic ray chart of the world.
I see.
The chart of how the intensity depends upon longitude, latitude, and altitude.
And from the preliminary data that you've received from Explorer 1, are you finding about what you expected to find?
Well, during the past 12 years, we've made high-altitude rocket measurements up to about 100 miles at over a wide range of geographical position, so that we haven't so far been surprised by anything we've learned from the Explorer. The Explorer instruments are working well. The measurements fit in well with our preliminary explorations. They are vastly more comprehensive, and every day we have more measurements coming into us and a much fuller picture. So the real point of the satellite measurements is their comprehensiveness.
And it might be interesting, before we go to the instruments, to find to look at one of these charts here of the data as it comes to you.
Yes. The original information is actually recorded on a magnetic tape recorder in each one of a number of stations. Now, on this globe, you may have notice
Yes.
these little white
Perhaps
spots.
it would be good to look at that.
Point these out first. We have these now. These little white spots show the stations, the location of stations around the world at which we have receivers. Now, all of the information from the satellite is transmitted by a very tiny radio transmitter. And now these are very specialized radio receiving stations, and this is called the picket fence, this chain from here down to here. It's a rather irregular fence, but it is known as the picket fence. Now, every time the satellite passes around the Earth, it must cross this picket fence someplace.
Yes.
So at least one of these 10 stations has an opportunity to receive the signal on each pass.
And at these points, the recording is on magnetic tape.
Yes, that is correct. There's a magnetic tape, a high-grade magnetic tape recorder in each station, and you might be interested in some of the others. There's a cluster of stations in California. There's a station in Singapore, one in Australia, and one in Nigeria, one in South Africa. These are the principal stations in addition to the North America, South America chain.
And then I gather that the magnetic tape is played and through an oscilloscope, and these lines result.
Yes, the magnetic tape is played back through an audio filter and finally comes out on this recorder. Now, you can see this looks like a rather zigzag line, and each time it moves from the upper position to the lower position corresponds to the reception of 16 counts on the Geiger counter. Now, this piece of record represents about 2 minutes of recording on one pass over a station in California on the first day of the Explorer 1. That's the record of the result.
Now, all of us have, I'm sure, have a great deal of interest in the vehicle which carries these instruments. And while I gather that we don't have a Explorer 1 here in the studio, we have a thing which roughly represents its size and shape.
Yes, well, this shows how every man can make his own satellite using a stovepipe. Now, this is intended only to illustrate the general size and form of the satellite. Now, I think there's been a considerable misunderstanding about this because the satellites we have been planning in the United States have been planned to be spherical.
Yes.
And those are the Vanguard type. Now, this is the Jupiter C type, a rather accurate representation of the Explorer 1, both in diameter and in length. So this gives one a feeling,
This would be
I think,
roughly 6 inches and something over 6 feet in height.
Yes, that's correct.
And now, what about the instruments which are aboard?
I have a photograph of the complete apparatus that was flown. Here's the photograph.
Oh, yes.
And the most interesting part, so far as we are concerned, is this tube. Now, that's a Geiger tube.
Yes.
Now, the scale of the drawing is 6 inches just to fit inside the stovepipe, and about 40 inches overall length. Now, within that little set of instruments, we have a vast number of small parts. The experiment is one, I should say, which might be considered a simple one in general conception. It's very simple, namely to measure the counting rate of this Geiger counter as exposed to the radiation above the atmosphere. The counter itself could be imagined as being an object of about this shape and size, this actual size.
And then I take it that because of the development in transistors and this sort of thing, it's possible to, I guess you would say, miniaturize this equipment.
Yes, so in fact, 5 years ago it would have been totally impossible to do this experiment because of the great weight and power requirements of electronic components. But for example, here's an ordinary vacuum tube as used in commercial radio equipment. And here is an object of almost the same size as one of our transistors which supplants this. Now, it's not only a question of size, but it's a question of weight, and it's more particularly a question of power required. And there's been a vast revolution, really, in electronic components during the past 5 years, which has been necessary to make such an undertaking possible.
Yes. Now, how were these instruments developed here on campus?
Well, originally I outlined the general scheme of what I'd like to do with a satellite, the physical principles, the nature of the measurements we'd like to undertake, and I went over this with George Ludwig, who's one of our graduate students in physics, and he's been carrying the ball ever since and actually doing the detailed design, the necessary checking, the full details of developing the apparatus.
Now, I know that you could answer the following question: all my life, but how long has this been in development?
Well, very specifically for about 2.5 years. And in a general way, our work over the past 10 years has been, so to speak, working up to it in the way of general preparation.
So that this represents really about a 10, 12-year interest of your own.
Oh, yes.
And in the last couple of years, this has been, of course, brought to fruition.
Yes, been very intensively worked on for 2.5 years.
Yes. Now, I gather that in another Explorer, there will be a very small tape recorder.
Yes, that one we would have liked very much to have in the first Explorer, but the change of plans in the national program and the schedule were such that that was not possible. But in the second Explorer, in fact, on board the one that was fired on the 5th of March, we did have such a tape recorder, and we hope to have one of these on board the next one also. I can show you some of the pieces. All of our actual recorders are now in California, where they're the final assemblies being made at the Jet Propulsion Laboratory. But here are some sample little components. Now, these are some of the gears. These are really clockmakers' parts. Here's a miniature ball bearing, which is used in the recorder. Here, for example, is the little clock spring, which is used to drive the tape back after the record has been made, and so forth. Now, the whole recorder slips in a can of about this size. That's the final overall size.
In other words, this is probably the smallest tape recorder that's ever been built.
Well, I'm really not sure of that, but I think it's in the running, all right.
Yes.
Certainly, it's a very specialized recorder for this purpose.
Yes. Well, now, as a scientist who's interested in basic research, perhaps you won't object if I ask you, now, what are the practical results of these experiments which are taking place?
Well, our early experiment, now our first one on cosmic ray intensity, from this experiment we will determine in due time as the data flow in and we are able to plot them and make up our full chart, will give us a chart. Might be thought of something like a topographical chart of a piece of land. And we'll build up this chart showing the intensity at various points around the world, as complete a chart as possible. And from that, then we'll submit that to scrutiny and interpretation along 3 different lines. In the first place, the gross features of symmetry about it should bear on the nature of the Earth's magnetic field. That's probably the dominant feature. And secondly, any deviations from the simple model required theoretically by the Earth's field will indicate the nature of magnetic clouds around the Earth. In other words, this is a tool for exploring the astronomical environment of the Earth and learning what kinds of clouds of gas and magnetic fields exist in the solar system. And thirdly, the way in which the intensity depends upon altitude gives us a very good idea of the spectrum of the radiation and the way in which what we call albedo radiation from higher latitudes is funneling back and forth from one pole to the other. So this is all in all an experiment of very considerable geophysical and astrophysical interest. Now, I shouldn't like to represent it as having anything to do with the daily life of man in the near future, but I do think it's clear that the more we understand about the nature of our astronomical environment and about our own Earth, it's quite likely the more we'll be able to do about it and do with it.
And this is not unknown in the history of the world, is it, for
well, it's very common in
basic
science
research to become eventually to have practical applications.
Yes, I think there may be examples of fundamental knowledge that's not been useful, but they're not at all common. For example, Isaac Newton's book at the time it was written was The Height of Impracticality,
Yes.
but of course all of mechanics depends upon these principles.
To change the subject quite abruptly, is space travel feasible or more feasible as a result of what's being found at the present time?
Well, I think this is a very small start in the subject, actually, and we could say that in a way we have already achieved space travel.
Yeah.
However, as I think you do mean actual transport of human beings to other objects, celestial objects, the moon and Mars and so forth, well, we can certainly foresee now that we do know that it's possible in principle. We know that it'll be a very expensive undertaking. There are a great many enthusiasts for pushing this. Whether or not the human race wishes to spend its efforts in this direction, I think isn't yet clear, but I think as scientific people we can certainly say that it is possible.
Yes. Now, for a number of years you've been chairman of the National Rocket and Satellite Research Panel, and
Yes.
over this period of time you gentlemen must have reached some conclusions about where all of this leads us to.
Well, I think this is a very broad question, actually. We can speak with some competence about the technical and scientific possibilities in making more satellites and what they can be used for, and in the practical possibilities and the magnitude of the undertaking required for space travel. I think it's also evident that there'll be enormous implications on our intellectual and cultural life as human beings. It's perhaps part of the reason we exist, if we have any reason for existing, is to do things of this character. Now, I think most of us, of course, are interested in the very first instance in having enough to eat and having a shelter, and of course we're no different than animals in that respect.
Sure.
Now, if we have our heads for any purpose, I think it might be to put them to work on some such more imaginative undertaking. So as you can see, I'm very enthusiastic about the exploratory prospects of space travel, but there are many economic and political questions also involved, and these are questions for men of very great breadth of experience in human affairs. So I don't like to minimize those aspects,
Yes.
although they are quite commonly neglected in many discussions.
Yes.
And I may say that I believe there's a tremendous amount of nonsense floating around these days, and that one should cast a very critical eye on this before he plunges into it.
Well, thank you very much for coming up here today, Dr. Van Allen, taking time out of what I know is an exceedingly busy life to explain some of these things to us and to the people who will view this film.
Appreciated this very much.
You have just seen Explorer, featuring Professors James Van Allen and H. Clay Harshbarger. This is another in the series, At the Frontier, presented by the State University of Iowa.